Let's start off. Hope everyone tried this. Can do have few answers. 5 mu square by 12. Yeah. Yes. So once you see from IR perspective, it becomes quite easy to solve. So here we already know this point is going with U. This, let's call it B. This is also going along the rod. So we have 2 points whose velocity or directions we know. So drop the perpendicular here. Drop the perpendicular here. This point will be your IIR. If this is 120, 30, 30, this angle is also 30. That means this angle is 60 and this angle is also 60. This is actually an equilateral triangle where this will be length L and length L. Is that making sense, everyone? So IAR and the point A and B are forming an equilateral triangle. And what is omega here? You can take velocity of A and the perpendicular distance is L. So omega is U by L. And for this rod, the center of mass is here. This would be the perpendicular distance D, which is height, which is L root 3 L by 2. So moment of inertia about IAR will be I center of mass plus md square, which is ml square by 12 plus m into root 3 L by 2 ka whole square. This would be 10 ml square by 12. 5 ml square by 6. Kinetic energy of the rod. So you can stand on the IIR and it feels as if, it's pure rotating about that point. So half IIR omega square. This is the kinetic energy of the rod at this instant. Now look at the steps. Making sense. So in order to find IR, you need to find at least, you should know 2 points whose velocity or directions you should know. Drop the perpendicular, the point where they meet is the IR. Go and stand there. You will see everything is going in a circle. That is the whole point of IR. You can get omega from there, IR, and then you're done. Clear? Any doubts on this? Yeah, Vihan, Poroja, Ansh, 3 of you got it. Next one. Next one. So we have our disk here. This is going with V, rotating with omega. There is no slipping. A is the topmost point. B is the horizontal point. Radius is R. Find the radius of curvature of A and B. Radius of curvature is a concept from circular motion, if you remember. Find the radius of curvature of point A and B. It's not slipping, right? So V is equal to R omega in this case. And what is G here, God? It's a ring rotating. Let's see. Now remember, radius of curvature, how do we find? Now, the radius of curvature is given by V square by the perpendicular component of acceleration, isn't it? So you need to ask yourself, when this thing is going with omega, if you look at the topmost point, this thing has a velocity V plus R omega, which is nothing but 2V. This point has a velocity V this way, and R omega here, which is also V, this is V root 2. So these are the velocities of these points. What about the acceleration? This guy is going in a circle. Remember, there is no A and alpha, but it is going in a circle. So we have omega square R. This is your perpendicular acceleration. Here, since you're going in a circle, you'll have an acceleration omega square R toward the center. But you need to take the perpendicular components. So this is 45. If you take this component here, this will be a centripetal, which is omega square R cos 45. This will be a tangential, which is omega square R sine 45. So if you remember, while finding radius of curvature, velocity V and A, you don't touch the velocity, you keep the velocity as it is. You resolve the accelerations into components. A cos theta, that will behave like A centripetal, and A sine theta behaves like A tangential. At least that's what the particle thinks. So from this logic here, if you see the radius of curvature of point A, the speed will be 2v ka whole square by omega square r, but I know v is equal to r omega, so this is 4r. And the radius of b will be v root 2 ka whole square. You have to take the total speed by the tangential component omega square r cos 45. This will be 2 root 2r. Now, one thing you have to be careful here. Generally, I have seen people do a mistake. They think IIR is the radius of curvature. They say, sir, you're saying it is rotating about this point. So the radius must be 2r. Understand one thing. What is IIR? It is a point about which the body will be in rotation for an instant, right? Every instant it is changing. The radius of curvature depends on the path, isn't it? Radius of curvature depends on the path in which the particle is going. Radius of curvature depends on the path and has no relation to the IIR. So radius of curvature is defined for the path. Radius of IIR is defined for a body. But you can see actually the answer will come always double. So that's it. Just be careful with this. Someone asks you for radius of curvature, don't try to use IIR. Both have no relation at all. I mean, just to show you, in case you remember, this thing actually follows a cycloid path. Remember, we did this in kinematics. We even calculated the distance traveled by that point in one circular, this thing, one revolution there. This forms a path like this. So what we are finding here is at the highest point, this would be the radius of curvature. So that part is belonging to this. So this is your center. This is 4r. Making sense? So it actually depends on the path. There, have a look at this. And if you remember an acceleration profile, we saw if a particle is going in a circle, it will have a center of mass, we'll have r alpha, and we have omega square r. Since it is going with v and omega, so there is no acceleration from there. You only have this omega square r. So there, just be careful with that. This thing has nothing to do with IIR. If they ask you radius of curvature, this is one way to do. Do you guys remember the formula? A mathematical way to find radius of curvature? Yeah, R is 1 plus dy by dx whole square whole power 3 by 2 by d square y by dx square. There is a mathematical formula that we derived in radius of curvature. So, all clear with this? Next thing, angular momentum. L bar. So, in entire rotation mechanics, right, this is the most important one. Has a, I won't say it is tough, but what I realized, right, most people don't know how to calculate angular momentum, and that's the reason they find it little tough. Today, we'll be focusing primarily on calculation and some basic conservation problems. So, first thing, if you take a particle, the angular momentum L bar is given by m r bar cross v bar. This can be also written as r bar cross mv bar. Mv bar is nothing but momentum. There. So this is the relation between. So r bar is a vector, just like torque is r cross f bar. This is a vector from axis to the particle. P bar is your linear momentum. This is the relation between linear momentum and angular momentum. Now, how do we calculate this? So we can write L bar mr cross v bar as mrv sine theta. Just like torque we did, we can do it two ways. So if you take this is v, this is r bar, this is axis. Extend the line, drop the perpendicular. If this angle is theta, this angle will be theta, this will be r sine theta, which is r perpendicular. So angular momentum can be written as L is equal to m into r perpendicular into v. Remember torque we did this thing, torque is r perpendicular into f. Or, so this can be taken as mvr sine theta. So that become mr perpendicular. Or you can do this. Resolve the velocity into components. This will be v cos theta sine theta, which is v perpendicular. So you can write angular momentum also as mr v perpendicular. So both are right. Both will give the same magnitude. Either you keep v as it is, drop r perpendicular, or keep r as it is and get v perpendicular. This is how you will get the magnitude for a particle. It's exactly similar to what we did for torque also, r perpendicular into f or r into f perpendicular. So this gives you the magnitude. And how do you get the direction? Again, the same way we did for, this thing. We'll assume r bar as a rod and see how the r bar rotates right clockwise or anti-clockwise, and then we use right hand thumb rule. But we need outs on this page. So this is the angular momentum for a particle. And for direction, assume r bar is a rod. and see the tendency of its rotation and use right hand thumb rule. And if this is R bar, this is your axis, and if this is V bar. Now you tell me, if R bar is a rod, which way will it go? Right side or left side? Meaning itra, so you can see and tell, right? It will go to the right side. What direction is this? Clockwise. So the direction is minus k cap. Now which will the rod go, up or down? We know it will go up. This is anti-clockwise. Thus, direction will be exactly the what we did in rotation. Torque, we do the same thing here. This is plus k cap. So direction matters a lot. So this gives you the magnitude, MRV perpendicular or MR perpendicular V, one of them, and this gives you the direction. There, we know how to calculate angular momentum for a particle. So let's see a few problems on this. Any doubts on this? Let's see a few questions. We have a particle here, mass m. It's going with speed v parallel to the x-axis. This point is your origin, 0, comma 0. Let's call this 0, O. Let's call this point A, which is 0, comma D. Let's call this point B, which is 4D, comma minus D. Let's call this point C, which is minus D, comma 60. Find the angular momentum about ABC, OABC. So depending on where you're standing, you can have different angular momentums. So just like torque, when I say what is angular momentum, your first question should be, sir, about what axis? Try, take a minute, get the one on two ones, and then I'll show you how to do. But you try on your own for a minute. Remember, you have to give me the magnitude and the direction. Mm, Direction, Mihan. Let's see the first one. Let me show you a few. Then I'll give you 1 more minute. So if you talk about O, this particle is going with U mass M. Extend the line, drop the perpendicular. So if you drop the perpendicular, this will be D. So angular momentum about O will be M into D into U. What about the direction? It is going this way. If you assume the D is the perpendicular this, then it is rotating right side. So the direction is minus K cap. And this point is A. Angular momentum about A is 0. Why? Sorry. V bar passes through the axis. Just like torque, if the force passes through the axis, there is no torque. If V passes through the axis, perpendicular distance is 0, or you can also say V bar is parallel to R bar. So cross product will be 0. Clear what we done? So can you do for C and D, B and C also? Try them. I'll give another 30, 40 seconds. That's it. So extend the velocity vector, drop a perpendicular, and see the direction. Let's see. So this is the velocity. Extend the vector. B is somewhere here, which is 4D comma minus D. So from here, drop a perpendicular. This distance will be 2D. Now, if you see, this thing is still rotating this way only. So angular momentum about B will be M into U into 2D minus K cap. Similarly, if you talk about C, if you extend the vector and drop this thing, this will be 5D, na? Because this total height was 6D and minus D there. So L about C will be M into U into 5D. Now be careful, direction is plus K cap. Because see, from C, if this is your R perpendicular, and if this was the velocity, you can clearly see this thing is rotating upward. So this would actually be plus K cap. So be careful with the directions. Magnitudes are easy to find. Clear, everyone? Next one. Next one. 2 kg mass moves with 10 meter per second along the line 3x plus 4y plus 1 is equal to 0. Find the magnitude of the angular momentum about the point 1 comma 1, or let's say 2 comma 3. Doesn't matter. I just want the magnitude. Okay. Try others 30, 40 seconds more. Hmm. 76. Let's see. Now in Max, did you learn this thing? Perpendicular distance formula. The perpendicular distance from a point to a line is given by ax naught plus by naught plus c by root over a square plus b square. Now, if you know that, you're done. So this is the perpendicular distance from x naught comma y naught to ax plus by plus c. So the perpendicular distance would be 3 into 2 plus 4 into 3 plus 1 by root over a square plus b square. That would be 6 plus 12, 18, 19 by 5. Therefore, the angular momentum is m r perpendicular into v. 2, 19 by 5 into 10, 76. Easy? Any doubts on this? All got this? Next one. So that is for a particle. Direction, it depends on which way you're going. Na? That's why I didn't give you. I simply said you're going on a line. Then the confusion comes, are you going that side or this side? So both the directions are possible. So next thing is if you take pure rotation. So if you have a body rotating about a hinge or an axis, consider a particle mi going in a circle of radius ri. Then we know velocity vi is equal to ri into omega. So angular momentum of this particle will be mri into vi, which is nothing but mri square omega. So angular momentum of the system will be sigma li, which is sigma mi ri square into omega, which nothing but becomes I. So there, if you look at the formula here, so angular momentum about an axis is given by I about that same axis into omega bar. This is valid only for pure rotation, like it's rotating about a hinge or some fixed axis. And you can see the formula, it kind of looks like, P is equal to mv. Angular momentum का प्लेस में linear momentum, mass का प्लेस में I and v का प्लेस में omega. So if you actually see the physical significance of angular momentum, it is same as linear momentum. Linear momentum talks about translation, angular momentum talks about rotation. So higher the angular momentum, more difficult to stop the body from rotating. That is the physical significance. There. So we know how to find for rotation and we know how to find for translation. Then from there we can actually find even for rolling bodies also. We'll go that way. Next thing. All clear with this? Now, if you see the formula, it kind of looks like F is equal to dp by dt. So here F is dl by dt. Now L bar is nothing but I into omega. So this can be written as I into d omega by dt plus omega di by dt. So this is actually the actual formula. I d omega by dt plus omega di by dt. Now here if I is constant, then d omega by dt is 0. Then our formula becomes I is equal to d omega by dt. D omega dt is nothing but I alpha. Just like Newton's laws of motion, F is equal to ma is valid when mass is constant. Same way, torque is equal to I alpha is constant when I is constant. Now, most of the cases I doesn't change, so we have never had a problem. We will see later on, I can change. So this formula which we are writing, torque is equal to I alpha. If you see, this actually kind of looks like this: mdv by dt plus vdm by dt. Similar one. So this torque is equal to I alpha, which we are writing, is valid only for constant I. Clear? So then, so we have torque is equal to dl by dt. If you shift that side, we'll get integral dl bar is equal to integral torque dt. This is nothing but delta L bar is equal to integral torque dt. This is change in angular momentum. This is also called as angular impulse. I hope you remember impulse in center of mass. There is a change in linear momentum. So if you see the relation there, it kind of looks same. So there it is delta p bar is integral f dt. This was change in linear momentum. This was linear impulse. So be careful. Linear impulse, angular impulse, both are different. And this symbol was J. Angular impulse has no symbol. That means if you give me a torque versus dt graph, so area above S, this is a positive area. This is a negative area. So area under tau t graph will give you change in angular momentum. Just have a look at this. Just give me a minute. So if it's kind of looks like area under ft graph was change in linear momentum. But the better thing would be this. So we know delta L bar is what? Integral torque dt. Now torque can be written as R cross F dt, but F dt is nothing but impulse. So that is R cross J bar. There, this is the relation between angular impulse and the linear impulse. Angular impulse is given by integral R bar, the position vector cross J bar. Quite a useful one. We're going to see problems based on this later on. So this was linear impulse. This was angular impulse. So that means whenever you hit a body or something, you not only generate linear momentum, but you also make it rotate. When you think of like this, if I have a rod here and if you go and kick the rod here, won't this rod rotate also and translate also? So this rod actually starts going like this. It does both. There, have a look at this speech. A bit of a theory. Any doubts on this? Next thing. So we have torque is equal to dL by dt. So if torque external is 0, implies delta L bar is 0. So angular momentum doesn't change. Therefore, L bar is constant. Basically, this is your third conservation, law of conservation of angular momentum. The first was energy. You can do that when work external force is 0. Work done by external is 0. The second was linear momentum. You can use that when the external force was 0. This you can use when the external torque is 0. There, now you have total 3 set of conservations. And where did you hear the word angular momentum first time? Atomic structure. Angular momentum is quantized. MBR is equal to NH by 2 pi. That was the first time you actually heard in chemistry. So if torque about any axis is 0, then L bar about that axis is conserved. So be careful there. You can't conserve angular momentum about whatever point you want. There. So we know how to calculate for linear bodies. We know how to calculate for pure rotation. Now we will for rolling bodies, and we also know the conservation of angular momentum. Like I keep saying, if you know how to actually calculate angular momentum, that is like 80% job done. Next one. Let's see. Angular momentum for a rolling body. Remember, whenever you hear the word rolling body, they're indirectly telling you there is one translation plus one rotation. But like I showed you that, swinging table fan wala problem, it is not necessary. You can always have, multiple degrees of freedom. So don't blindly mug up the formulas. Understand whether what kind of thing is there in the system. Is it only translating, rotating, or what? So if you have a body going with V and omega, you know the standard stuff. We split this into pure translation, as if every point is going with V. Then we rotate about pure rotation about center of mass. So we first of all treat it like a particle at the center of mass, and then we treat as if the center of mass is fixed like a hinge. So angular momentum of a rolling body is angular momentum of center of mass. So you treat the center of mass like a particle. Angular momentum about center of mass. So this is M, R center of mass cross V center of mass plus I center of mass into omega bar. So you have to go and stand on the center of mass, and then you think it is pure rotating. Kind of like energy only. If you remember, energy was the same formula: kinetic energy of center of mass, kinetic energy about center of mass. There. Now let's see how to calculate for rolling bodies. Have a look at this. Any doubt so far? Not clear with anything calculation? Great. Let's see a question. We have a disk, mass M, radius R. It is going with V and omega. There is no need, for no slipping condition. It can go with slipping, without slipping. It doesn't matter. Angular momentum doesn't care. So I'll give you 4 points now. Let's say we have a point A here. We have a point B here. We have a point C here. So there are 3 points there. Find the angular momentum about ABC. So the definition of axis is important. You should always say from where are you calculating it. So if you stand at A and look at this body, what is the angular momentum? B and C. Get them. I'll give you a minute, then I'll show you. Then I'll give you one more, we can see more. Direction matters, everyone. Directions are important. Just don't randomly get the magnitude. You will go up. It's fine. Try. Take a minute. Get a wrong one. It is okay. Let me show you. Then that's the fastest way to learn. Should I show you one? See. So this is point A. This is velocity. Extend the line. So treat the centromos like a point. Drop the perpendicular. This is R. So angular momentum about A will be angular momentum of center of mass, meaning you treat the all the masses at center of mass going in a line, plus angular momentum about center of mass. Go and stand on the center of mass and think it is rotating. This would be m into r into v. Look at the direction it is going this way. That is minus k cap, and you're rotating with omega this way, plus ICOM omega minus k cap. So omega is also going anti-clockwise, so that's also minus k cap. So MRV minus k cap, plus it's a disk, so mr square by 2 omega minus k cap. Yeah, that's how we find it. If this is going with v, this is point B. You can clearly see the velocity is passing through this, so the translation component is 0. The second part will be ICOM omega minus k cap. So one thing you will notice, no matter which axis you take, the rotational component is always same, because you always go back to the center of mass and calculate it, right? So the rotational component will be always mr square by 2 omega minus k cap, no matter where you stand. Similarly, if you stand at C, drop the perpendicular, this will be the perpendicular distance. So angular momentum about C will be mrv, direction becomes plus k cap, plus this would be mr square by 2 omega k cap. There. So if you see in C, actually both the components subtract. In B, there is no transition component. In A, both the components add up. Please check. Ask me if you're confused. This is how you calculate for a rolling body. Anyone not convinced with anything here? All clear? Devika, Jainil, Arnav, Arush, Sharman, clear with this? Adi, clear? Ahana, let's see one more. Top view. We have a rod here. Mass M, length L. Rod is going with V here, rotating with omega this way. This is point A. This is point B. This is point C. This is point D. This distance is L by 4 from the center. So meaning this rod is like, rolling and going like this. It's like your pen game. If you take your pen and hit it in this corner, it rotates and goes forward. No? Get this? Find angular momentum about ABCD. Should I show you? 30 seconds more, then I'll show you everything. Then you can verify whether you got it. Let's see. So I'll write the values to check out your answers. So angular moment about A will be MBL by 2 minus K cap ICOM, which is ML square by 12 omega plus K cap. This will be MBL by 4 minus K cap. Like I said, the rotational component will literally remain always the same because it is angular momentum about center of mass. You always go back to the center of mass. This guy translation would be 0. There, I think if you got this, you actually know how to calculate angular momentum for rolling bodies now. Check it out. Anyone not clear with anything particular here? Clear? All got this? Next one. Remember the swinging table fan? We have a disk, mass m, radius r. We have a rod, mass m, length l. This is rotating with omega 2. This whole red setup is rotating with omega 1. Find L bar above the system. Now this, you can't use that formula, angular momentum of center of mass plus about center of mass, because there is no translation here. This is a rotation plus rotation. So your degrees of freedom does matter. Try. If you observe here, you won't get a constant angular momentum actually. This thing has a angular momentum which is changing with time. Let's see. So we can split this into two parts. So basically rotation and revolution. So this is rotating with omega 2. So this angular momentum, let's call it L1 bar, which is I omega 2, which is mr square by 2 omega 2. And if you see, this is actually not constant. If you see now, this vector, as the disk is rotating, this angular momentum is also rotating. It's like this, isn't it? When this is rotating, so this direction is changing continuously. It is an xy plane, but direction is rotating. Whereas if you look at for this guy, let's call it L2. So we have to find angular momentum about this axis. So this will be I of the rod plus I of the disk omega 1. So L2 will be rod is ml square by 3. Disk, you have to use parallaxis theorem from here. Mr square by 4 about the diameter plus ml square parallaxis theorem into omega 1. This will be j cap. It is actually acting upward. So you can't add them directly. So the angular momentum of the system will be mr square by 2 omega 2. This is a vector which is rotating. But both the components are perpendicular. If they ask you for magnitude, you can square them and add them. This would be mr square by 4 plus 4 ml square by 3. Omega 1 upward direction, I'll take it as j cap. So if you want magnitude, this square plus this square ka root. So actually this is the similar basis, I think in 2018, I guess, they did ask a question in rotation. There was a question like this. There was a disk here and there was a disk here and this whole thing was rolling on the floor. So the idea was the same thing there. So this is rotating about this axis. So this is one angular momentum. And this whole setup is rotating like this. So this is another angular momentum. So basically I have to find the resultant of L2 and L1 with an angle theta. You're getting it? Then we take a vertical component will be L2 plus L1 cos theta. And the horizontal component is L1 sin theta. L1 sin theta is rotating. Now, people who didn't know that it is rotation plus rotation, they got goofed up. They tried to use the formula, angular momentum of center of mass plus about center of mass. So there is a problem like this in PYQs, advanced PYQ. So when you do, you will see that. But idea was this. It's based on the degrees of freedom. You have to actually split it. Is this clear, everyone? The same thing we did with energy also, if you remember. That was slightly easy because there was no direction you can add it up. Have a look at this page. Next one. Any doubts? Ansh, Daksha, clear? Niharika?
Sir, could you again explain how you got mr square by 4?
है डायमीटर का डिस्क का क्या होगा रे गॉड perpendicular to the plane mr square by 2 na in the plane mr square by 4 particle is projected with u and theta mass m. This is the origin. It is going in a projectile motion. Gravity is there. Find angular momentum of the particle about the origin at time t. We'll ask two questions. Wait, when it reaches h max, that would be a standard mains question. And at time t. How did I get j cap for both? It is rotating in which plane? XY plane, na re? Omega 1 is rotating in which plane, re? Roja. XY plane, na? So perpendicular to that is that, sorry, it's not xy plane. This is x, this is z, and this is y. So it is rotating in xz plane, isn't it? So perpendicular is j cap, isn't it? That way. Clear, na?
But sir, omega 2, it is rotating in y and z plane, right?
I have taken this as x, this is y, this is z. So it is rotating in this plane, na?
No, sir, but the disk, when it's rotating about its own axis.
That you ignore, na? That we don't care. I'm talking about omega 1.
Yes, sir, omega 1 is j cap, but omega 2 के लिए it will be I cap, right?
That is changing, na? इसीलिए I draw it like this.
Yes,
It's
yes.
not constant. It's not constant. It is changing every moment. Hmm? Yeah. Both are not j cap. Give it a try. You have to give me direction also, na? Purvaja, the direction part is clear, na? No, I never wrote j cap. Where did you think I wrote j cap? See, look at this circle thing. How did I draw?
Yes, sir, yes.
Uh, hmm. Get this, get this. Let's see. First was easy. So when it is at h max, the velocity will be u cos theta. Extend the line. You want about this thing, drop the perpendicular. This would be your h max. So angular momentum will be m into perpendicular distance is h max, which you know u square sine square that by 2g. Velocity is u cos theta. Be careful, direction is minus k cap. Always give the direction. Don't forget. You can substitute the value of h max. You know how to do that. What about the b part? Now b part, you can do brute force. M is equal to m r bar cross v bar. You should know your values from kinematics. So what is r bar? Position vector. U cos theta time I cap plus u sine theta t minus half g t square j cap. u cos theta I cap plus u sin theta minus gt j cap. There. Once you know this, it is just a matter of cross product. So when you do cross product, I cross I is 0, j cross j is 0. So basically, you have to do I cross j and j cross I. So we get L bar is equal to u cos theta into time into u sin theta minus gt, and I cross j is k cap plus, when you multiply j cross I, this will be u sin theta t minus half gt square into u cos theta. J cross I is minus k cap. So there, simplify u square sin theta cos theta t minus u cos theta gt square minus u square sin theta cos theta t minus plus हो जाएगा वो gu/2 cos theta t square, this whole into k cap. This guy goes off. You end up with minus u gu cos theta t square by 2 minus k cap. There, that's your final answer. I forgot a mass also into m. There, that's your angular momentum at time t. This is much better way to do this. But this is brute force. Nothing clicks like R bar, V bar, from kinematics, put it there and finish off with a cross product. Okay, let's see what to do the alternate way. Now, alternate we know torque is dl by dt. So change in angular momentum is integral torque dt. So when you projected this with u and theta, at any instant, if you see the only force acting is mg, agreed? And this would be the perpendicular distance, which is u cos theta into time. So therefore, torque will be mg u cos theta into time minus k cap. So now if you integrate this, we will get mg u cos theta t dt minus k cap 0 to time. This would be L final minus L initial. L initial is 0 because it is initially passing through the origin. This is mg u cos theta t square by 2 minus k cap. There, you get it in one step. This is 0 since b bar passes through origin. So you have to be careful. It gives you change in angular momentum. Here initially it became 0. Therefore, L final is this thing. Yeah, but it should click that you can do like this. Sometimes it doesn't click. Exam ke that flow mein, then it doesn't matter. It might take a minute more, but shouldn't at least out to it. Clear with this? Same answer. Clear with this, everyone. Take a break. Come back with 7-7. Any doubt so far?
So can you show the previous page?
Hmm.
Thank you, sir.
Okay, come back in 10 minutes. Next one. So we have our conical pendulum. Mass m. This is a string of length L. Going in a circle like this. This angle is theta. This is O. This is O dash. So O is the center of the circle. O dash is the point of suspension. This is a good one, right? I'll show you how they can frame and advance more than one choice question. But before that, first angular momentum about O and angular momentum about O dash. This is going with speed u. So particle is going in a horizontal circle, conical pendulum. Hope you remember that we did that in circular motion. Okay, get the next one. Let's see. So if you actually try to first see about odd O, look at this. So at every instant, this is the velocity. This is your R bar. So if you see R cross V bar, this is your L bar. Can you see how is the angular momentum? It's out of the plane. So when you're here, this is your R bar, This is your velocity vector. This is your L bar. When you're here, velocity is this way. This is your R bar. This is your L bar. So if you see here, L bar is constant. So this will be m into v into radius, where radius is nothing but this guy, which is L sine theta. So this is mv L sine theta. Direction will be upward. I'll just show this an upward arrow, or j cap, whatever you want to call it. And if you see, this is constant. And it makes sense also why it is constancy. Now for this particle, if you actually draw the free body diagram, you'll notice we have tension, we have mg. That's it. There are only two forces. This is there. So if you resolve this into components, we get t cos theta and t sine theta. And if you take this point O here, you can see torque about O is zero. No? T cos theta will balance mg, they will cancel out, and t sine theta will pass through the center. So if the net torque is zero, then angular momentum has to be constant. Is that clear? What about O dash? O dash is an interesting one. This is your O dash. This is your R bar. This is your V bar. You can clearly see this thing is going out like this. It's like a crown ka shape. It is out of the plane. This is your R bar. This is your V bar. This is your L bar. Meaning, if you look at the angular momentum, it kind of looks like this. Like a crown. Is that making sense, everyone? And what about the magnitude? Magnitude is constant actually. So if you take LO dash, that will be m into u into L only, because the perpendicular distance is L. But the direction is not constant. It is continuously changing. This is how the direction would be. Magnitude is constant, but direction changes. Have a look at this. Let's study a little more on this. So same particle, you can see suddenly it is constant. It is not constant about some other point. Yeah, mg component causes torque. But there is a thing. Now look at this. If you actually try to calculate the torque, see how it is. This is your R bar. This is your V bar. This is your L bar. You know how is the torque? Torque is which way? So when you take about O dash, if you look at the forces, we have tension, we have mg. So tension is passing through O. So torque about O dash will be mg ka torque into the perpendicular distance, which is L sine theta. And what is the direction? Look at this. Mg rotates this way. It's actually out of the plane. Mg sine theta, right? In this thing, it is coming out of the plane. How to show this? kind of K cap. It's not actually K cap, that's the problem. Because as the particle rotates, it keeps on going out of the plane. So you know how it looks? This way. Torque is tangential. This is the plane, na? It's perpendicular to this plane, isn't it? Torque actually looks like this. Torque is tangential. So at any instant, this is how it looks. Torque is this way. L bar is this way. And if you see torque and L bar are perpendicular, torque is perpendicular to L bar at every instant. Both are changing direction, but every instant it is constant. Again, this is about O dash we're talking about. Now, can you see some kind of resemblance? This looks like if force is perpendicular to velocity bar, this is what? Uniform circular motion, na? The magnitude of speed remains constant, but the direction changes. The mod V bar is constant. But direction changes. So if you use the same analogy here, you will notice we got the same answer actually. Angular momentum ka magnitude is constant, but the direction changes. Is that making sense? So here also, if you see L naught dash ka magnitude is constant, but direction changes. It resembles. And not only that, if you look at the components also, this is one component, this is L parallel, and this is this thing. So L perpendicular. This guy is changing, and this guy is constant. So even within the angular momentum, there are two components. One component is changing and one component is constant. This is a component parallel to mg. I'll do one thing. I'll just call it L parallel. This, let's call it L perpendicular. This is perpendicular to mg. Have a look at this. There are too much information is there. Matlab, first thing, the main idea is this: the torque will be actually tangential. That is the main idea there. So, and if you look at this at every instant, the torque and the angular momentum are perpendicular to each other. It is similar to uniform circular motion where force was perpendicular to velocity or momentum. If force is perpendicular to velocity, the magnitude cannot change, but direction changes. So same way, angular momentum ka magnitude is constant, but direction changes. हाँ Vihan.
Sir,
हाँ.
sir, I couldn't understand how is mg tangential, whichever part of it is causing it off.
Which way it should be according to you?
So like
Mg is rotating this way. God, how will this rotate? If this is R bar and this is mg, rotation is this way, na? It's coming out of the plane, isn't it? Torque.
yes, sir.
So
Okay.
coming out of
Okay,
the
yes,
plane,
sir.
मतलब कैसे दिखेगा?
Okay, sir.
So
Understood.
here, ये है ना plane. So when you are here, this is the plane, na?
Yes, sir. Understood.
So it is always perpendicular to that plane.
Hmm. Thank you.
Hmm. I know it can be confusing diagram, na? This is O, that is O dash. So it's perpendicular to this plane. This is perpendicular to plane O, O dash, and that mass M. Let's call it whatever is the particle. So this was O, O dash, and this was particle. Sure, everyone? So it's a good one actually. If you see that O dash looks pretty innocent, MUL sin theta, but has a lot of stuff. These are all are literally a question in the exam. Huh? The angular momentum is perpendicular to the torque. So let me show you how they'll frame that question. But any doubts on this page? This is how the question will be framed. They will say torque is equal to A bar cross L bar, where A bar is a constant vector. No information is given, it's a constant vector. L bar is your angular momentum. Options will be like this. L bar is constant. Mod L bar is constant. Component of L bar along A bar is constant. You can say like this, L bar is variable. And they'll ask you some few questions, like few options like this. Which of the options are right? It'll be a more than one choice question. Now, if you relate this to the previous question, you will realize A bar is like mg. Mg vector is constant, no matter how much you rotate, mg doesn't change. Take a minute, think about it. How do you relate this to the previous one? Now, look at this thing. First of all, it is given torque is A cross L bar. Great. But we also know, now that means what is this? Torque is perpendicular to L bar, na cross product, isn't it? If you do cross product, A cross B is perpendicular to both A bar and B bar. Do you agree? And we also know torque is dL by dt. So now you tell me, if torque is perpendicular to L bar, since torque is perpendicular to L bar, the magnitude must be constant. And this is similar to force perpendicular to velocity bar. Mod V is constant. But if you apply torque, angular momentum must change. Therefore, the direction must change. Magnitude is constant, but direction changes. Now, if you go from that option, first option is gone, second is right, L is variable. The C ke liye, so if you look at this, what do you call in conical pendulum, it is that vector only mg bar. Now you can relate this to the conical pendulum problem. Or you can say like this also, mathematically also you can go. Torque is also perpendicular to A bar. Therefore, component of angular momentum along A bar cannot change. Is that making sense? If you apply torque in a particular direction, then angular momentum in that direction will change. Agreed? Is that statement making sense? If you apply torque in a direction, then angular momentum in that direction will change. Now you're saying torque is perpendicular to A bar. That means there is no torque in A ka direction. Therefore, angular momentum along A cannot change. Therefore, there is no torque component along A bar. Even if you don't know conical pendulum, you can still figure it out. Therefore, component of L bar, it won't change, meaning if there is already some value initially, it will remain same. Now, if you look at this with the conical pendulum problem, you'll realize mg is that. So even C is right. Is this clear, everyone? It's a pretty good one. It looks like easy one and all, but there's a lot of things that you can ask in this. So do have a look at this. Clear. Next one. Next one.
The answer will be BC for this.
B, C, D.
Okay.
L is also variable, no? Magnitude constant, action state. We have a rod here. This is a hinge. Mass M, length L. Gravity is there. So on top of this, there is an insect or an ant. The ant is walking with some speed u. And this rod is rotating with omega. Now, interestingly, what we observe, after some time, now because of gravity, this rod will start going down. This angle is theta. The insect has walked till here. Let this distance be x. And the insect speed is u at this instant. And for some reason, omega is still constant. Now think about it. If I leave the rod, shouldn't it go with increasing speed? But for some reason, the speed is not increasing. So an ant walks along the rod with speed u. We observe the rod rotates with constant omega. And we need to figure out why is that. Why is the rod not accelerating? Find u in terms of x and theta. Anyone not clear with the question? Any doubts on this? Take a minute, think about it. Why is that omega not changing? Right, yeah. That was what was happening. Let's see. First thing you need to understand, when this insect is going, something else is changing here. So when this ant is here, mass m, did I give the mass m? Mass is m for the ant, small m. Forgot. And let the distance be x. So if you take the moment of inertia of the system, it is ml square by 3 for the rod. Remember, this is the axis, so it is still rotating in this plane. Don't use ml square by 3 sine square theta 1. Plus the insect is mx square. So the moment of inertia is changing here. I is changing. That was a catch. So if I do di by dt, this would be 2mx dx by dt. Dx by dt is the speed of the insect. So the actual formula is this: torque is equal to I d omega by dt plus omega dA by dt. So all the torque that we are generating is actually used to increase the moment of the compensating for the moment of inertia. So here omega is constant, so this term actually becomes 0. Making sense? Now can you try? There, I got the idea there. Try, I'll give you a minute. Now you need to find torque as function of theta and equate it. Done. Get it. How much will be the torque? Insect ka weight is mg, your weight is capital Mg. There. The torque also will depend on x and theta. Get it, get it. I'll give you another 30-40 seconds. See, the torque will be mg L by 2 cos theta plus small mg x cos theta. That is equal to omega into 2mxu. There you know everything except u. So shift it, you'll get the answer. mg L by 2 plus mgx cos theta by 2mx omega. There. Easy? But question is easy. But the headache is, to figure out that the I is changing. Most people won't realize. They should know the torque is di by dt. Any doubts on this? So there, now you know how to calculate angular momentum for particles, for rolling bodies, for pure rotation, even for different degrees of freedom equation. The next thing will be angular momentum conservation. So we will see some basic problems today. This is a standard model. We have a sphere Rotating with omega, mass m, radius r, solid sphere. Due to internal forces, generally happens in stars. It shrinks to r/2 radius. Mass remains same. Find a new omega and find the change in kinetic energy. Now remember, if the net torque is 0, then the angular momentum is conserved about the axis. Since it is internal forces, there will be no torque. Let's see. Since the external force is 0, since torque external is 0, L bar is constant. Therefore, I1 omega 1 is equal to I2 omega 2, which is 2 by 5 mr square. Omega is equal to 2 by 5 m r by 2 whole square omega dash. So omega dash will be 4 omega. It actually goes faster. And what about the change in energy? Now, see, I can write like this. I know kinetic energy is half I omega square. Multiply and divide by I. This will become I omega whole square by 2I. This is actually L square by 2I. Kind of looks like P square by 2M, isn't it? So L is constant. Now what is happening to I? I is decreasing, so energy increases. So change in kinetic energy will be K final minus K initial. So this will be L square by 2I final minus L square by 2I initial. You can calculate this. It actually increases. Yeah. That is the same reason. If you see, right, in ice skating and all, this is one of the phenomena they use. Have a look at this.
This is a demonstration of the conservation of angular momentum. I have a couple of, looks like 5-pound dumbbells in my hands. I've got a platform.
Able to hear? Is there audio coming, right?
That spins freely on its axis. I'm going to stand on this platform.
Can you hear? I can't hear actually. Can you guys hear the audio? You can hear, na? Chalo, theek hai.
And then have my able assistant,
there.
David,
So we have
come
Dr. Berg
over
here.
and give me a spin. And then what I would like to do then at that point, I'm going to start with my arms out and then see how close I can bring the weight into my chest.
There, so he's standing on that
Okay.
rotatable thing. He's going to push. Now see, now he's pushing, right? Now when the hands are very far, what is happening? Moment of inertia is more. Now if you bring the hands closer, I will decrease, so omega should increase. So look at him.
You can see
Can
my
you see
tie
his speed is
flying
increasing?
up. So
Look at
flying
that
up.
again. Slow, when he brings it closer, it goes faster.
You can see my tie flying up. So ice skaters use this principle.
Can you see that? So that actually is true. It is not some of our imagination there. You can actually try this in your society. You'll find this merry-go-round. So if you have in a local park or something, you can definitely try. So you spin. That's like your disc rotating. This guy jumped on it. So he's just standing on the corner. This takes 3.2 seconds. Now see, he goes into the center. So I is decreasing. Did you see it speeded up? This thing is going faster. This thing took 2.3 seconds only for rotation. Now if he goes to the edge and if he stands outside, देखा slow हो गया? Because when he's leaning outside, I increased, omega decreased. It took 4.13 seconds. So this is a very simple thing you can try in your society also if you have this thing.
Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skill through years of
So when they
tireless
rotate
training,
like this,
skaters must learn to understand and
now
use
look at this
angular
girl when she's
momentum to
rotating.
become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity.
So by stretching the legs and the hands, they're changing the ICA value.
When the skater is rotating with no net external torque acting on her,
There.
angular
So basically by
momentum is
stretching the leg, I
conserved.
is more.
With her
When she
arms
brings
and
it
leg
closer,
outward,
omega
she
increases. She goes
her
faster and
moment of
faster.
inertia, which reduces her angular velocity. As she pulls her arms and leg inward,
There.
she is
Did you see
able
that
to
speed?
spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
With angular momentum. There. This is also one more example. This is from the International Space Station. You can see he's floating.
Hi, my name is Mike Fox.
Go ahead directly.
And no external. Watch this. I'm actually
Yes.
doing a little bit of a demonstration here, so I want to tie myself up in a knot.
Yes. So he's going to spin himself. Now he stretch. He's keeping the hands close. Now when he stretches, did you see? He will slow down. He's going now. Bring the hand close again. He goes faster.
Again, what's going on?
I'll
is
post
that
these
as my
videos in the
body's
group. You guys can check it out. So there. So this thing, what we did right now, right, is not our imagination. It does actually happen. Clear with the question? Let's see one more. We got a disk here rotating with omega. T is the thickness, mass m, radius r. Then what you did, you took another disk of radius r by 2, same thickness and material. Is placed on it. What is the new omega? So initially the disk is already rotating with omega. Now you took another disk of mass of radius r by 2 and you placed on top of it, same thickness and same material. What will be the new angular velocity? This is another standard model. Question is clear? Vihan, I'll punch you. Omega will increase or decrease? If you add more mass, will I increase or decrease? I increase. तो omega तो decrease होना चाहिए. How did you speed up? Why? Why are you becoming a pioneer of energy creation? Nee, Devansh, you goofed up. Ansh, you are right. Nee, Adi, that is wrong. You guys are messing up the mass or something. Nee, Vihan, that is wrong. If the radius becomes r by 2, mass becomes m by 4. Mass of the disk is not same. So you mean to say, if you and your sister go to the shop and there is one big pizza and small pizza, you give the small pizza to your sister, she'll accept it. Same mass, na? Kya problem tha? Try this and see. So torque external is 0. Initial angular momentum I1 omega is equal to I1 plus I2 omega. This will be mr square by 2 omega. So the main catch here is this mass becomes m by 4 because mass depends on area. So this moment of inertia will be mr square by 2. Now see, the other one is also a disk. Mr square by 2, but m became m by 4. R became r by 2 by 2. I hope you're getting it. Mass becomes m by 4. So omega dash will be 16 by 17 omega. There, easy one, proper mains level question. People do goof up, they take the mass to be same. That's the thing you have to be careful about. Next one. Any doubts? Easy. But be careful, mass won't be same. Next thing, we have a cone like this. The bottom is open. Let this be R. Let this be 3R. The height is H. Gravity is there. Now what you did, you projected here a particle of mass m tangentially with speed u. What do you think will happen? This will start going down. This will start spiraling like this. So find a u minimum if it doesn't come out from the bottom part. Niche is it is an open surface, so from lower opening. So this will actually keep spiraling inside. So it will come till this corner. And then when it comes here again, it becomes something like tangential, and again it starts climbing up. This is actually stuck within this shape. It can't come out, it can't go in. Now you need to ask yourself, why is this doing like this? Meaning, who is making it go up again? Our lower radius is R and upper radius is 3R. Think, it's a good one. Think, I'll give you 2 minutes. First try to figure out why will it go up. Meaning you could have solved the problem without knowing that, but it's always better you have an idea what is happening. Think. Take a minute. Let's get some water and come. Did you figure out who is actually helping it going up? Ask yourself. When this is coming down, will the speed increase or decrease? Speed will increase. Now, if the speed increases at any instant, look at the forces. We have a centrifugal force, mv square by r, and mg. As you're coming down, speed is increasing, r is decreasing. So centrifugal force is becoming stronger and stronger. Now, centrifugal force ka component in this direction will dominate mg ka component, na? So as it keeps coming down, the speed is increasing, r is decreasing. So centrifugal force becomes greater than mg ka component. Then it starts going up. But once it starts going up, speed will decrease, r will decrease, mg will again dominate. Again, it starts coming down. You're getting what is happening? If you keep going down, centrifugal force dominates. If you keep going up, mg dominates. You're stuck between these two. You can't get out, you can't go down. So it's a fight between centrifugal force and mg. Technically, that is what is happening. Is the thing clear why it is stuck between that thing in the ball? Again, it is smooth ball, so there's no loss of energy. Anyone not clear with this logic, what I said, please ask. So that is the reason why it is stuck. That is fine. Now we need to find u minimum so that it doesn't come out from the ball. So if you take about this axis, look at the forces here. At any instant, we have centrifugal force mv square by r. This is passing through the axis, and we have mg here. Now observe clearly, torque due to mg is in some other direction. Torque due to mg is out of the plane. Right? And torque due to mv square by r, mv square by r is passing through the axis. Meaning mg ka torque na is like this. You're getting it? Mg ka torque is like this, but I want torque about this axis. So there is no torque actually. Torque about the axis is 0. Now remember this thing. If they ask you is the torque 0, torque is not 0. But torque about this axis is 0. Is that making sense? Mg is giving torque, but that there is no torque in this axis. So that's what I'm saying. If the torque is 0 about a particular axis, then angular momentum is conserved about that axis. Therefore, angular momentum about this axis is constant. So let this point be particle velocity v. So this will start spiraling. So when it comes here, at this point, it can have two speeds, vx and vy. But vy is 0 since you asked for minimum speed. Means if you go faster than this, it'll come out with vy. Or you can say since it doesn't come out. Since you don't want it to come out, the vertical velocity must be 0. State 1, state 2. Conservation of angular momentum. L1 is equal to L2. Initial angular momentum mv3r. Final angular momentum mvxr. Vx is equal to 3v. Conservation of energy. Energy in state 1 is equal to energy in state 2. Initially, it is half mv square, half mvx square. There's also potential energy initially, mgh. So shifted that side, Vx is 3V, so that would be 9, so 8 mvx square by 2. There, so Vx is equal to root gh by 4. Why am I finding Vx? I need to find V now. I wrote wrong. This is V only. Check. Previous page here. This is the question. So we have a a cone kind of thing. There is an upper opening radius 3r and lower opening is r. So someone projected a particle with speed u inside. So this will start spiraling like this now. So as it is spiraling, if you give enough speed, there is a possibility it will start coming up again. So it is stuck between the upper and the lower part. It can't come out. So the question is find u minimum so that it doesn't come out from the bottom. And Puraja, what happened? If there's an mg, then there will be a net velocity. No, see, you're forgetting. If you see in this direction, there's a normal reaction also, Nare. We are looking at velocity along that, n is also there, na?
Yes, sir. Yes, sir.
Is this clear, everyone? There, it's a good one. So this is how angular momentum conservation will be there. That's what I'm saying. If you know how to calculate it, it's just a matter of putting L1 is L2. But first of all, you should know how to calculate. So next class, when we catch up, we'll do more tougher problems. So these are some basic, we'll do few more basic problems and we'll go for some tough ones. So next Tuesday, when we catch up, mostly I think we should be able to wrap up the chapter. And after this gets over, we'll start off with heat and thermodynamics. So, okay. So that will wrap up for that day. So we almost did 72 questions, everyone. So do go through the whole thing. I think by the time we complete, we will touch 80 plus. So do start solving. We're almost done. Like, in case you have not started solving, you should start solving. It's a lot of work. Okay. With that, we'll wrap up for that day. So I'll see you on Tuesday again at 5:40. So any doubts, anything, stay back and ask. Also feel free to leave. So take care.